hear me? And how is the sound?
Yes.
Tim?
Yeah.
Hello.
Yeah, hi. All right. Well, somehow I see that um uh, within the, a bit strange. So if there is a problem with the action itself, just let me know, and then maybe I will just switch off the camera. Um, so to save a bit for the stream of the screen share. Okay. Well, I suppose I need to have the screen sharing. So my Windows system. Can we see it? Is everything great?
Yes.
Okay, great. And material, which is related to data compression. Well, like I warned you, there was data compression, and well, I will finish this during today classes, so there will be even another topic we will overlook. But let's okay. Well, maybe the first of all, I would like to ask you guys, compression daily. What would you say?
I'm sorry. Could you turn off the camera? I don't know. Probably my internet's bad. I'm hearing you bad.
Okay. Okay. So I will stop sharing the web camera. Okay. Now it's being turned. Okay. Well, guys. Mm-hmm. Uh, so, so my question: where daily do we use the data compression? Who can tell me? Yeah, that could be WinRAR. What else can we mention? Maybe something besides the WinRAR.
A zip file.
Yeah, okay, zip files. What else? Okay, Mindaugas wrote pulling files into one folder. Well, it's not really the compression itself, but maybe something in addition. Any thoughts, guys? What about data materials we use daily, like pictures, music, some movie files, and so on and so on? Literally, things are more related to pictures because for example, if we will take the Paint software, right? And we would have, for example, some image. Well, let's just say image of, well, let's suppose just a white canvas, right? Well, we would be able to save that. And let's take a look. Well, for example, let's consider the first three formats like a PNG, JPG, BMP. Well, let's suppose we will save them in those three different file formats. Let's just make this assumption. We will do that. Okay, so we'll be having a BMP, we will be having a PNG, and we'll be having a JPG. Can we be sure that all of those three formats represent an image? Is it so?
Yes.
Well, yes, it is so. But what makes them different? And before going forward, let's take a look on parameters of such images we have, and we will be badly surprised that literally there is a difference based on the size of them. So a BMP took around 2 megabytes for storing that white canvas. And some of you would say that, well, the picture itself was not very big, right? It was relatively small, like this one, right? Which Frankenstein is kind of a normal picture pulling that on the website. The size is kind of normal one, but at the same time, it takes 2 megabytes, which is over than the recommended size for images, showing them, let's say, on some websites, because 2 megabytes is a huge file actually. And in the same time, JPG and PNG, they took a much smaller amount of space, let's say, for storing the image, and we can make conclusion that JPG has the super small size, and PNG has well, a bit bigger size than the JPG, but slightly um, smaller than a BMP. So what makes them different? Well, BMP is image 7 format without any type of compression, without any type of method that tricks the system in order to compress data. And JPG is literally JPG is the method for data compression that allows to lose information during compression. So you always open a JPG file, zoom in it. In most of the cases, you will see that, well, that there are some mildy areas. There are some reddish and bluish halftones making an literally that's just a post effect of the JPG compression method, and PNG is the compression method without losing data, so you can always see the original information, and there is no big deal how much you zoom the picture, it will be always the original one. So the same thing happens with video materials like movies. There are different formats, and same happens for the music, where we have different formats like WAV, MP3, MP4, and others. They have their own formats, and some of them losing original information, some of them not losing original information, some of them can be even used with some of them even assumes zero compression at all. So literally, what we'll be doing today, we'll be overlooking three algorithms. Two of them are frequently used in 7-zip. And we will take a look like how it works. What can we do with that? Well, I suppose, especially this material will be really useful for you because you will be capable to create even your own compression methods, for example, based on methods we will overlook. Okay, so the introduction part here will be the same as I just told you. The different aspects where we can use compression, and that can be even used not only for pictures and music, but just for the data. Some of compression methods based on psychovisual effects, which is a pretty cool topic, let's say openly, but we are not gonna overlook that. But I really recommend you to find out some info about this, because it's really interesting one. Okay, well, we know that compression literally is needed mostly for fastening information transfer, right? Maybe sometimes to store more information than without a compression. That would be understandable, and mostly society develops two types of decompression methods. Surely there are even subclasses of them, but mostly from the lossless class of compression methods and lossy compression methods. If we are talking about regular life of computer user, well, we know that there are a lot of some sound effects, some music, some pictures we overlook daily, and what literally helps us to have these compressions and decompressions happening. Literally, those are codec packs. Well, for example, you cannot really take a look on the you cannot really um, run an AVI movie without the AVI codecs, for example, right? Some of them mostly been installed with some movie players like VCL player and others, but mostly we can even find out codec packs on the internet, and surely there are some really popular codec packs. Well, we can Google for them. That will be um, pretty easy. For example, one of the most popular ones is a K-Lite codec pack, which is frankly saying no known thing, right? For most of us, I suppose. Well, that's the thing. So literally, it contains a lot of functions that allows to compress and decompress information, and that's literally how it happens, and that makes it's possible to see some movies, to see some specifically encoded images, um, play some music files, and so on. Okay, well, to get this maybe a bit more practically, how we can represent a lossless compression methods and lossy compression methods. Well, loosely compression methods, they're oriented on the minifying the size of the result. And for that, there could be specific equations used, and there are some roundings of data of values are going to be used, and that makes it impossible to restore the original data. But lossless compression methods, in its essence, literally compresses data without any ideas about making the final result smaller by the size. The main thing is to restore the original data. So that's why, for example, PNG images, they take more than JPG, but in the same time, you cannot see the original image in the JPG from the JPG file, but from the PNG file you can use, you can see the original file. What we are gonna overlook? So here we have one of the most popular compression methods, like the Runlen, Hoffman-Trees, Lampolsky-Welch algorithm, which is one of super popular ones in 7-zip, because 7-zip invented, as far as I know, the second version of the Lampolsky-Welch algorithm. And we have Lucy methods, which at least we're not going to overlook at this time, but maybe we will take a look on these formats maybe in one of next times. Or let's see if that will be interesting for you, how they are working. For example, JPG. Well, maybe I can show you how it works, because I have this full set of the equations used there. Okay, so maybe well, what else we can talk about? Well, we can talk about types of compression methods based on the approximate time which will be consumed by the method. So there are such things as symmetric codec and asymmetric codec. Literally, a difference between them is very simple, and both of these classes, they are inside lossless and lossy compression methods. So it's kind of sub-split of their groups. And idea here is super simple. So symmetric codec allows us to at least approximately inform a user after which time the method will be finished. And asymmetric literally doesn't allow it. But as practice shows, asymmetric codec is more efficient than symmetric. But users don't really like this because literally it's impossible to predict approximate time and well which will be needed by the method, and that makes it a bit problematic. So that's why asymmetric codec is not really used. We have to specifically activate them and specifically say to our systems that we're using asymmetric codec. Well, we have to know their names, we have to know functions from where they're stored, and so on and so on. So maybe we won't be overlooking this at this moment. And there are even several methods of so-called codec works, like syntactic methods, semantic methods, and a hybrid method that involves both of them. But in this case, probably we won't be overlooking these methods and difference between them at all, because it will take, I would say, enormous amount of time for us. So let's try to do things which would be practical for us. Okay, and maybe the first of the methods we will be overlooking will be the Runlen encoding. This is the super simplified case, which mostly nicely works for binary codes. Do you know binary codes?
A little, it's like 1 zeros, 1 zeros.
Yeah, exactly, yes. So in other words, those are machine codes that allows us to represent existence of the electricity on the cord by its state, where 1 means there is electricity, 0 means there is no electricity. And literally, because computers based on the cords or wires, if you like to call them that way, that makes communication between spare parts of computer components. So that's the only way to describe information, and and combinations of data that's gonna be transferred between them. So that's why we use binary codes as the lowest or machine-like information. Okay, anyways, for binary codes, it works very efficiently. For let's say symbols like textual characters, show you the idea. So here we have a couple of modifications of this method, and let's overlook the most simplified one which was invented literally a few decades ago. Well, not really few, but it was developed like 4 decades ago, which was used in the most simple computers. So let's make an assumption that we have the textual line like A, double B, double C, 9D, and so on and so on. And such text literally has, well, some amount of symbols, right? But what is interesting, we have some symbols repeated. So literally that we might say that we could be capable to replace this chain of symbols by just mentioning the symbol and amount of them as repeated symbols. Like we have to mention and we have to split both symbol and amount of repetitions. Like we have this symbol, we have dash, for example, saying that after that we're gonna have amount of repetitions, and we will have amount of repetitions. And that could happen for only the cases when it's reasonable. For example, if we have 9 letters, so we have 9 bytes, and we're converted them to 3 bytes, so we have a benefit of data compression. So from 9 bytes we go to 3 bytes. But in cases where we have just one symbol or two symbols or even three symbols, it's not reasonable to do that, because when we have one symbol or two symbols, we will have three ones, right? We'll have, instead of one and two, we will have three, which is not practical. So we have something opposite than compression. And when we have three symbols and we receive three symbols, there is no need to spend computer resources on this. So we had 3 bytes previously and 3 bytes afterwards. So we do this mention of symbol and its repetition only when it's practical. Does it make a sense, guys?
Yes.
Okay, but this is the one of super simplified methods which was used from the very beginning. There are even another cases. For example, this case, when we store a couple of symbols for amount of repetitions, but in the same time we mention all of the repetitions. For example, amount of all of these symbols, we have this small n appearing, right, between A's and M's. But we still mention amount of repetitions. So this is another approach. And which approach to use in the particular case is actually based on our thoughts. Okay, well, what else could be modifications? Well, the next amount of modifications would be based on some repeatedness of information. Let's suppose especially for the binaries, when we have amount of repetitions, we can calculate how many zeros do we have and how many ones do we have. And we can literally combine those numbers. Well, this method might be a bit complicated, because literally we are storing information of zeros before each of the ones, or before the end of the line of bits. But I suppose idea is clear. So we are collecting amount of zeros reaching 1. Then after that 1, we again collecting zeros, and we write info about that. Again, we have 1, and amount of zeros before the next one. That's gonna be 0. So we place a 0. Nextly, we go after this one, and we collect how many zeros do we have there, and we write that info. Surely there might have been an information if we have 1 in the end of the symbols chain, of the bits chain, and that's frankly saying would be somehow specifically created value that would say, okay, we have 1 in the end, and if there is no such value, then it would mean that there is no 1 in the end of this line. So is this example clear for us, guys? Yes or no?
Maybe.
Maybe. Okay, so take a look, please. We have 14 zeros, right?
Yeah.
Do you know how to convert numbers from decimal to binaries? Yes.
No.
How? How could it be no?
I mean, 14 zeros, how to convert to binaries?
Yeah. How to convert 14 to binary code? Do we know that?
Yes. You
Really,
have,
yes?
like,
Or I'm guessing that I know.
I'm guessing that I know.
You're guessing. Okay,
I would
do
need
we need
a paper to count it, but I
okay,
think I
okay,
could do it.
okay. Do we need some small reminder how to do this?
Yes, please.
Okay. Well, in this case, I will take material which I show in another university. So give me a second. I will load that. And I will show you how these conversions happening. Because actually, if you will apply this particular method for compression, so you have to be capable to check if you did everything correctly. Okay, give me a second. I will try to find this out. Uh-huh. Okay, well, I found this. Okay, great. So I will open, and here we have data about numbers. Well, let's move forward and all this. Yeah. Well, for example, we will start then from the beginning. So let's suppose we have the number 1987. How can I prove that this number is 1987? What could be a provement of this? Well, the primary we have to know which numerical system this number is written in, right? That's gonna be the first thing we have to ask. Nextly, if that's the decimal numerical system, then we are capable to split that number in such pieces. Like 1 goes for thousands, 9 goes for hundreds, 8 goes for decimals, 7 go for ones. Literally here we have an equation for this. But what is the generalized form? Well, literally rewriting this equation in a generalized form, we could have the following equation that literally allows us to split the number in components and still prove that's the number in the numerical system, in particular numerical system. Okay, well, let's move forward a bit since it's just a small reminder for you, which you had to know previously. Well, let's suppose you would need to convert the number to the decimal numerical system. What would you do? And by the way, it's just decimal if we assume to have decimals. If we want to convert the binary number in some other numerical system, that would be possible as well. So what we're doing? We have the binary code and we converting that to decimal numbers. So we have each of these digits as multiplier of the base of the number, which means amount of variations per a symbol in original number in the power of that values or that numbers or that let's call it symbols index. An index starts from the right side going to the left side starting with a 0. So this one will get a 0, this one will get 1, this one will get 2, this one will get 3, and a numerical system inside which we receive in which we receive the final result based on the way how we write this amount of variations, because for decimal numerical system 2 can be written as the 2, but if we would try to have the binaries, we don't have 2 as the digit in binaries. In binaries, we have 2 only in the way of 1, 0. That's it. There is no other option. You know, it's like 10 in decimals, in decimal system. But it's 1, 0 for binaries. Does it make a sense?
It does. It does.
Okay. So in binaries here, we would say that this one is going to be multiplied with 1 and triple zeros. Here it will be 1 and double zeros. Here it will be 1 and a 0, and here it will be 1. So that's the case. For example, well, what would be if we would try to convert, let's say octal value to decimals? Well, we would take 1, 4, 3 as multipliers. We will take the base of the number, which is 8, because we have 8 variations per symbol. Well, in octal values, it varies between 0 and 7, so there is no value 8. So there is no digit 8 in octal values, because it's like there is no digit. And I want to highlight digit, not the number, but digit of 10 for decimal numerical system. Because decimal numerical system is amount of digits per symbol, which is from 0 to 9. Does it make a sense?
Yes.
Yeah. So what we do, we make this a calculus for multiplications, and then we just submit results, and we receive the value in the decimal numerical system. Well, frankly saying, all this would be an interesting until the case when we would have, for example, conversion from decimal numerical system to a binary. Okay, well, what would happen? Can we use the same method? And I would say we can, but that's gonna be a bit complicated for us to do that. Because the calculation itself will be the same, because this method is universal. Really, it's a universal method, but simplicity of this method happens only when we convert from the lower scale numerical systems to the higher scale numerical systems. But again, generally, this method works for every conversion in the same way as division works in the same manner. So division method is the method which is used for making conversion from the higher numerical systems to the lower scale numerical systems, like from decimals to binaries. How that happens? And by the way, this method works for every case, for every scale numerical systems. So what we do, we have 156. Well, we write 156, and we would like to have a result in binaries. So two variations per symbol. So what we do, we split the number with that amount of variations in the resulting number, which is 2. Okay, can we do that without reminder? Yes, we can. So we mention reminders, and once we reach the case when we have to have the reminder, we write that. So we decrease the value by 1, the remainder, and now we can split that. So we had 39, we received 38, and we divide 38 by 2 to 19. And again, we get reminders, and we make this calculus till the case when we have a 0 to be divided. And by that we can finalize our calculus, and then we can collect all of these bits going from the bottom side to the upper side. And we will collect them from the right to left case. Sorry, from the right to the left direction. Well, that's the method. But again, both of these methods work, and they work for whatever numerical systems. The only thing that for the one method we get benefits for calculus when we have one case, and the division method allows us to have benefits in another cases. But generally, both of the methods are correct. For example, what would happen in this method if you would like to have the number, let's say 156, as the octal value? What would you need to do? Well, well, all actions would be the same, but what would it be different? The different would be your way to calculate, because 156 in octal values split by 2 would not be the same as a decimal value split by 2, because we don't have to consider values we used to, like 8 and 9. We don't have them in octal values. Does it make a sense?
Yes.
So what I do frequently when we are working with numbers, I will show you one of basic tasks I try to give to every of the students when we reach this. But I don't know if we need to do this with you guys. Here we have multiplication table for hexadecimals, and we can grab one of multiplications, and I frequently ask users to students to show a full calculation process on the paper for making this multiplication. And for example, you can think of this task, and maybe afterwards in your free time you would like to maybe you would like to try it. Then take a picture of the slide if you like. So definitely that's gonna be kind of showing you a lot about how we're stagnated to decimal numerical system. So once we go outside that, we are incapable to make calculations, like basic calculations. It becomes very complicated. I'm not kidding, guys. You can make a picture of this table, and afterwards, in your free time, you can try. And believe me or not, you will be shocked about results. Okay. So by that we had a small reminder about these conversions. So let's go back, and here so we calculate the amount of zeros between ones, right? So here we have 14 zeros. Here we have 4 zeros. Here we have a 0 zeros, because we have no zeros between this one and this one. Does it make a sense?
Yes. Yes.
Okay, and then in the rest of the line we have another zeros. So it's 12. So you can see each of these numbers represent the amount of zeros before ones. So it's like we have such much zeros, then one comes. Then we have such one zeros, then one comes. Then we have this amount of zeros, then one comes, and then another amount of zeros, after which possibly another one will come. So right now, does it make a sense of this approach?
Yes.
Okay, that's great. And what's for the others? I will open the chat on another screen. So guys, somehow you look like shy to share your thoughts. So is this method clear for you? So what would you say? Okay, guys, I see that you are typing, so I will wait a bit. Once I will receive your texts. Uh-huh. Okay, sounds understandable. Okay, yes. Well, as I say all the time, literally, there is no difference in programming language. Once we are capable to imagine the algorithm, we can make that. Okay, and you can be sure that everything is all right. Um, well, I would say everything is good. Well, that's why we are working, and everything will be good. Okay, so let's go forward and know this. So this was another modification of the Sranlen encoding. Yeah, well, and there could be possible another modification, which was just mentioning a specific characters or specific values which we're about to compress. But again, such method is assumed to be a bit more complicated, so this appears a bit more rarely. Okay, well, what else there could be? So previously we overlooked from the beginning a so-called 3 bytes encoding, but there is even another method of 2 bytes encoding, which I don't really recommend you to try from the very beginning. Um, because this assumes that primary you have amount of repetitions, and after that you will be having just a value that's gonna be repeated. Value or a symbol, we can call it differently. So this method is a bit more complicated than 3 bytes method. But anyways, well, this method works really nicely. All the rest here is just a small reminder that once we compressed data, we had some benefit of that, which is a priori understandable thing. So guys, so what I will ask you to try on your own from the very beginning is to implement the runlen encoding on your own, and then after you will try to do that, we will make at least the first part for the encoding together, because once you are capable to create the encoder, you have to be capable to create a decoder as well. So let's start. So yeah, so your task will be to create both encoder and decoder. That works as the runlen encoding method. Let's suppose for 3 bytes. And don't forget that this line of symbols is just a text, and you are capable to get access to every indexed element of this text. And we already overlooked the ways how to go through the whole text, right? Okay. Do we need any maybe recommendations how to start doing this?
Yes.
Okay. So my personal recommendation would be the following. So once you will create the file of the Python, you can organize that how exactly. Let's take a look. Primary you can make an input of the text, or you can just make um, you can make just an original text. If you like, you can copy the text from this PDF. That would be nicely. And then you will need to have functions. Oh, let's call it. Let's call this encode. That has txt. That gives you back something. And you that again receive some text to be decoded, and then you will be given back some value. So afterwards, what you will be doing, you will have encoded text. That's gonna be the result of the encoding, and then you will be having decoded text once you run the decode function. And then after each of them, you can just mention what was encoded, what was decoded, and what was the original. For example, the following. That's gonna be one. So here it will be another one, and here you will have the third one. And then it has to be working in such manner so you would have the Python a.i, and okay, I have the problem with the name probably. Original text. It has to be there. Yeah, and you will just show those texts you will have. And surely here you will have the the encoded one, and after that you are converting this to you decoding this. What will happen here, guys? In the encode and decode functions. Well, for the encode functions, I would like to remind you that you can always go through the text, right? And you can always operate with that. And for example, you can use literally the element which is gonna be a result of the for in. That's gonna be one thing. But what else? Is there somehow we can use indexes? Using, for example, the same for in, and literally we can, because if we will be doing the following one, right, we will be working on these elements, right, which are symbols. In the same time, if we will be using, for example, something like the range of the LAN, just literally showing just literally showing that we are having the array from a 0 to um, to the len of the text. So we'll get the values between a 0 and the len of the text minus 1. So in other words, guys, you will be capable to work on the following. Or maybe let's call this LM as the index. That's gonna be maybe a bit easier. And if you see, and I bet you see, so we can get access to every of these elements by the index. And if you do that, right, well, we can always get to the uh, to the symbol, and for example the next symbol, and literally you can go to the next, and again next symbol, and just compare if they equal, right? Let's suppose what I will be doing. So I will be writing and if here finding out if the index is less than the len minus 1. So it means if I have a forwarding index, and what I'm gonna be doing here. So as you can see, um, we can always get the current one and the next one, right? And that's gonna be without any of the problems, right? And if you can do that, well, what makes it impossible to take a look if you have several symbols in advance? For example, having even more and more next symbols. All this is, frankly saying, possible. Like this one, right? And you can literally analyze the chain of them. And okay, I did all this in one row, but literally, since this is the another cooperation of symbols, right? You can always make something like the for loop, which goes forwarding, just finding out if each of the next symbols is the same as the current one. Does it make a sense, guys?
Yes, I guess.
Okay. So literally instead of this plus one, plus two, plus three, you can make the for loop. And actually, in my own implementation of this method, that's exact way how to do that. Okay. So guys, can I assume that you will start making this method, at least to try to make it?
Yeah.
What's about others? I know that it's morning and we all could be a bit sleepy, but guys, let's try to start working on all this. Okay, do we have any other questions? Or maybe we maybe might be unsure about some specific aspects of this method? If it's so, then please write in the chat or activate your microphone and let's have a small discussion. I see that Mindaugas is connected to the mobile phone. Can I assume that you will be working on the computer, trying to code? Okay, you're at the work. Okay, makes sense. Okay, that makes sense. After 3 p.m. Okay, I got your point. All right. So it is what it is. No worries. Okay, I got your point. So again, no worries. The main thing is that you would at least try things on your own, in your free time. If you will do that, that will be fine. But and again, it's only a recommendation from my side. Okay, guys. So those who can start trying to implement this method, so please try to implement this. I won't be disturbing you for some time. I assume it could be like at maybe at least 15 or maybe 20 minutes because it will take a time for you. But afterwards, I would like to know what is your progress and if you will need some a bit more time or it might happen we will need to have some another discussion about how to make this, how to make that. Okay, guys, so please start working on this method, and once you have some issues, so you stuck at some point, you can let me know in the chat.
Okay.
Okay, so I will need to write the task. All right, so I will do that in the Moodle then. So it will be available for you. So we have a few minutes before the break, guys. How's your progress?
Slow.
Okay, but if we are talking about only the function of encryption, what is the progress of the encryption function?
I mean, I'm getting somewhere, but I'm getting errors, but it's still doing something. So I'm just trying to fix something.
Oh, okay. But what if we will do the following? Well, let me show you. So here I used for in, right? So I use predefined. So I use literally predefined indexes, right? I will be going through, isn't it?
Yeah.
Well, yes, it is. So it can be even made a bit maybe differently, because or you can follow even this one. So when we go a symbol by a symbol, what can we collect with you? Well, we can have some helpers like previous symbol. That's gonna be whatever value from the beginning, and amount, which is gonna be some zero, right? So, and here you can literally figure out if you reached the previous symbol. So, if previous symbol is being found out, no, sorry, if the current one is the previous symbol, how can we do that? We have the text and we have the index, right? Then, if that's so, what we can say? Well, we can just say that we reached some additional repetition of the symbol, right? Is it so? So we can say that we're increasing amount by 1. Okay, well, Frank is saying that that looks great. Another thing, there could be else case when we're not reaching the current symbol, sorry, the previous symbol. So it's something new. If that's gonna be something new, oh, and you have to have the text, which is gonna be encoded text. So if that's a new symbol, then what you say? Well, you literally add in to the decoded text that previous symbol and dash and amount of repetitions, right? And in the same time, right now, since you have the new symbol, um, you have to say that right now you're having a new symbol which counts as the previous one, and you already have the amount of that equal to 1. Like if you reach the new symbol, you have repetition of 1 for that symbol. Surely here at this highlighted line, you would need to, let's say, find out how many repetitions were found out, right? And if it's practical to make this conversion, because maybe you just need to mention that symbol, which is the previous one, just once or twice or even 3 times, and that's it. At least I would do this in a such way. And after the loop, after this for, and for this else, you still have the same symbols right there, and all these tabs, they have to be converted to spaces. So, and here, when you reach the last symbol, well, you always will be, well, in some cases that's gonna be the same symbol as the previous one, or you're reaching the new one still. You're not placing this the last symbol into the encoded text. So literally here you can just check if the amount is bigger than a 0. So if something's been found out, then you can just add that previous symbol afterwards. the previous found out symbol, and that's almost the full solution for the encoding. Okay, I don't know, was it helpful?
A little, and for decoding, it's gonna be the same, just a few signs gonna switch.
No, for the encoding, I would say you will be going through the symbols and you will be looking for the dash. If you have a dash, then you have to take the symbol before that. For the amount of repetition, that comes after the dash. Otherwise you just print the current symbol. That's it. But firstly, please try the encoding. Okay.
Yeah, yeah.
Mhm. Well, as I said, I almost wrote you the full code for the encoding. It's almost the full code. Okay, anyways, I see by the schedule that right now we're gonna have the break for 10 minutes. Okay, so now it's 11 minutes, almost 12. So yeah, so let's continue at 22 minutes then. Let's have a 10 minutes break. Okay, guys. So I suppose we can continue. Put a plus if you're here, just to make sure that you are uh, that you are here and we can start working. Mm-hmm. Okay, so 3 pluses out of 4. Okay, let it be so. All right, so please continue working on the encryption function, and once you will have it, please let me know. And once you will have it, so I will have a small talk about decryption function, and then you will be working on decryption function. Okay, so how much time is it needed for you guys to finalize encryption? Maybe 10, maybe 15 minutes. How do you think? Okay, do we need to finalize encryption function together? Mm-hmm. Okay, what would others say? Mm-hmm. All right then. And then let's finalize it together. Okay. So at this point, if I will run this code at this point, what will I receive? Okay, I got problems because I have to because it's not possible to concatenate the number and a text. Well, okay, what can be done in this case? Well, I'm more than sure that you already took a look um, on the on the internet, but literally we have different functions related to data conversions. Well, you already know such functions. They are ints, strs, and others. Well, because you know the data types actually. So how can we fulfill our text? We can just fulfill our text with the str function to make it runnable. Yeah. The only thing we didn't receive that finalized text because the triple T was given back, so we have to give back triple T too. Okay, so what will be this one? As you see, here we're literally working on every symbol's appearance, right? That could be a space, that could be that previous character which had appearance of a zero. So all these things they have to be checked. But all the rest, I mean, things related to repetitions which have to be compressed, they are compressed. So the only thing it's compressed totally everything here in 3 bytes case. So let's figure out what we have to do here and what we have to do right there. So right here we have to firstly terminate the case when we are pulling the symbol inside in case when there is amount equal to a zero. And that's related to the previous character we have, which was a point, the dot, which a priori didn't exist in the in the system, right? So in the text. So let's see what's gonna happen. So you see, we terminated this out, this point with zero appearances. So it's out. What's next? So we have to take these cases of appearances of 1, 2, and 3, and we should do nothing with them. So which literally means that we will be working only when we have more than 3 appearances, right? So literally here, if I were you, then what would I do? Then I would take the case of appearances more than 3, and I will just write a text with amount of repetitions. So, and I would have the else case, and in the else case, I would do the following. I would be going through the following amount of repetitions, and for every amount of repetition, I would be just pulling a symbol. That's it, without amount of repetitions. And surely, since I have this tabulation sign, I will replace it with 4 spaces. So if I have more than 3, then I show amount of repetitions. Otherwise, I will go through those amount of repetitions, and for every case, I will add one more symbol. Literally, this code, this full code, has to be copied right there. For the case when I have literally, well, when I have finished overlooking a full text, and I have some amounts of symbols which are still unprintable. So let's see what we got right now. Okay, so as you can see right now, we have amount of repetitions only in cases when it's practical. So literally, that's the way how we can do this. So the question for you guys, if the solution understandable for you, what would you say? So what do you think, guys? So again, if you have some of repetitions and you have more than 3, then we show text, then we show a symbol with amount of repetitions. Otherwise, we don't show amount of repetitions, but for every repetition we show the symbol itself. That could be space, that could be just 1A, 2A's, 3A's. So it's just a regular, if statement, by which we just a bit differently create that encoded text part. And literally that's it. Okay, Edgar, so just take a look on the code. So you see, depending on different amount of repetitions, so we create encoded text in a bit different manner. If we have more than 3 repetitions, we show amount of repetitions. If we have less, then for every repetition, we just give a number. We just give a symbol itself, which is right here. So for every repetition, when amount of them is well till 3, so it would be 1, 2, and 3. We just give a symbol itself. And when such code is being run, then you see we have the same encoding result as we have in the presentation. And I don't know if this will help you guys, but I will maybe send you this file. Maybe that will be helpful for you. Let's see. Okay. So, and you have a link to the file. So guys, again, is this solution understandable for you? Because I didn't get the answer for that question. So what would you say?
Can I have a couple of minutes to look at the code?
Yes, sure. I can make even the text a bit smaller. So you would see, well, how to say the bigger part of the code. Yeah,
I mean,
the code.
you sent us the whole code, so
Yeah, sure.
well, I'm not gonna lie. When I look at it, it is understandable, but
Okay.
but if I would need it to write it myself, I don't think I have enough experience on programming to do it. So it would be a
That,
difficult time.
yeah, that means you have to practice.
Yes, yes, yes.
Mm-hmm. Okay. But overall, when you take a look on it, it's understandable, right?
I mean, yeah, I get the point, but as I said, like it would be difficult for me to do it.
Mm-hmm. Mm-hmm. Okay. Okay. All right. Well. I hope at least the same is for everyone else, because only trying and writing the codes, making mistakes, making some correct codes, you'll be reaching well, some sort of level. Only by that. Unfortunately, it's really so. It's not enough just to read a book about programming. Well, you have to program to make some apps. All right. So that was about the encoding of this text. So right now I will ask you to try a decoding. So what would be the decoding? So let's take a look. So you will be having such text, and you will be going a symbol by symbol right through this text, and what will make you capable to extract encoded symbols into a text line. Well, once you reach a dash, the symbol after which we have amount of repetitions, then you have to take the symbol next to which you have the dash, and you have to repeat that as many times as you have written that in the number. For example, you are reaching symbol D, that's your current symbol. If the next one is dash, then you have to take the symbol after the dash, and you have to make the loop. For example, for index in a range and that symbol like 9, and then for every of these iterations, you will be just adding um, a symbol to the decoded text. Yeah, and literally that's it. So the only you might be working with these indexes of the symbols might be not using for in, but maybe using some while loop. That could be one of possible ways. Well, how to deal with this, and that would be actually a solution for the decoding, for the decompressing. So how do you find a decompression? Is the algorithm itself is gettable, is understandable for us? What would you say? Let's suppose if you wouldn't need to write the code, is the logic understandable for us?
I mean, yeah, the logic is understandable.
Okay, and pointing to the cases of the current character and next after the next, is it understandable that we can just increase an index and that's it?
No.
Oh, well, how no? It's the same like we had a robot in the
I
cage.
mean, how do I say it? It's like easier said than to be done.
Okay, so here we have a decode, right? Okay, so so can we have, let's suppose, okay, the primary we will be having the text for decompression, right? Like let's say triple T2. Okay, so we would need to go through all of the symbols. How that's doable? Well, you can use for or you can use while. Well, maybe the while would be the best solution here. So while, let's suppose you have some I as the index. So while I is less than len of triple T, I mean while it's in the ranges, right? You'll be increasing I by 1, and you will be always like how to say getting to the symbols of I, all right? And you can always get to the symbol which is located next to I symbol, right? Like this one. Well, that works only in the case when we have the next symbol for sure. If you're somewhere in the end, then such thing is impossible. So let's make an if statement. If I less than len of triple T minus 1, only then it's doable. And let's see if we can access and we can get if the next symbol after the current one is the dash. If that will be written, if that will be written out, the dash itself, then, well, yeah, you see, the current symbol is D and the next is dash, so it's always possible to have it. Let's suppose if we would have, let's say, two symbols in the row. Okay, I wouldn't need to close the terminal, but no worries. So you can see, we can get, ah, right. So you can see we can get, oh, I didn't place +2, it was +1. Okay, let's run it again. So you can see we can have the current symbol, we can have the next one, and after the next one, right? So literally you can check what is the symbol after the current one. If that's the dash, so you can have the access to the symbol after that dash. If that's not a dash, then no worries. You have only one symbol to be given as the decoded symbol. Otherwise, you need to make the for loop for every of these repetitions mentioned here, like 9 repetitions. So you have to have the for loop that will add you in a for loop those 9 symbols of D. Does it make a sense?
Yes.
Mm-hmm. Exactly. Do you know how to make the for loop?
Yes.
Yeah. So there should not be a problem to implement this. Is there anything else we should discuss before you will try?
I don't know. I want to try it.
But you see that you have access to every of this data, right? The current, the next, and the next after the next. All right? Is it so?
Yeah.
Okay. So yeah. Um. Okay. So maybe I will hold this code available on the screen, so you can just take a look on it. If you like, you can rewrite this, and you can start modifying exactly this code if you like, for decoding the text, for decompressing, better to say. Okay, then I will give you maybe some maybe 15 minutes or maybe 20 minutes for this, and then I will write, as I did previously, an almost full code, which you probably could fulfill. And then after another period of time, I will show you a full solution. Then I will just fulfill that till the full solution. But firstly, please guys, try it on your own, because you need practicing. Okay.
Yes. Yes.
All right, guys. Once again, if you will face any issues, put your questions in the chat. Okay, guys, so time is moving forward. Well, like in all of the cases. So how is our progress related to the decoding function?
I don't know. I'm not sure how to properly use the for in this case. I'm trying, but
Um,
I'm still not getting
okay,
there.
okay. So the main problem is a for loop implementation, right?
Yeah.
Uh-huh.
I
Okay,
mean, I know how to use it, but maybe
but
I put it in the wrong spot or something. I don't know. I'm just trying everything now.
okay. Do we need any recommendations?
Yes, please, always.
Okay. Okay. So let's make another step in all this we have here. Um, we have the while. We are reaching to, well, we're checking if we can take a look on the right side of the symbol. So if there is if there are additional positions in the text, and we are looking on the right side. Well, how to make it? Well, let's call it more optimal. Um, the thing is that we would be able to take a look on the right side only when we have a symbol there. In the same time, if text is ending with the symbol, like a letter, so it's understandable for us that there will be no repetitions for that. Is it so? Can we see it in that way?
Yes.
Yes, and actually that's pretty obvious situation. So what we're gonna do? So if we have a symbol less than the last one, then we are capable to take a look on the right side. And if that's the last symbol, that's gonna be an else case. Oops, what's going on? Okay, I have to switch the keyboard layout. Okay, then we can say that the last symbol is just a symbol which will be added, which will be just added to a decoded text because it is so, and there is no other well possibilities. Let's call it that way. All right, Frank is saying that that's pretty gettable, but what happens here when we are not standing on the last symbol's position? Then, as we understand, we can always take a look on the right side because there is something, because we have some symbol on the right side, and we can compare it to a dash, right? So what happens here? We have two cases: the case when we have a dash, and the case when we don't have it. All right. When we don't have it, what do we need to do? It's just a regular symbol, right? The current one, the symbol at the position I. For example, if we have a text like this C, and after this C, and this is the symbol in the position I, so I plus 1 is not the dash, right? It's just another C. So this C, which is the current one we are pointing into, is assumed just a symbol which have to go to a decoded text scope. Is it so? Yes or no?
Yes, yes.
Yes. So yeah. So literally we're just copying this text and that's it. And if we will run this, what we will get? Ah, okay, we have problem with else somewhere. Okay, line 32. Let's find this line 32. Okay, it's this one. Hmm. So I have to have the same symbols as I have here. Okay. So some comment is needed. Some comment is needed. I will just place the semicolon um to make this. Okay. If it's just a semicolon, it does nothing. Okay, then I will just make this one. Just the fancy stuff, like a decoded text is equal to decoded text, just to be a comment. Okay, so what we got here, guys? We got here all of the symbols of the case when the next symbol of the current one doesn't have the dash. So what you have to do right now, you have to deal somehow with these cases, with these particular cases, where I place this comment. So somehow you should analyze amount of repetitions and implement them. So is this recommendation valuable, guys?
Yes,
Okay, so
but what are the
actually,
next steps?
well, actually, it's almost the final solution. It's almost. Okay, can I expect you for spending maybe another 10 or 15 minutes on trying to fulfill this solution?
I mean, yeah, I can try.
Okay, what's about others? Do others are fine for trying to make a solution from this point of the code? Okay, I see no reactions in the chat, but I really hope it means we are ready. Okay, so try to fulfill the code so it will be working with those amount of repetitions. So guys, the question is, how's the progress?
Well, I moved a little, but
A
I don't
little.
know.
Okay.
I'm not getting an answer. Like I'm getting the
Mm-hmm.
answer, but not the correct one.
Mm-hmm. Okay. All right. So we have some minutes till the lunch break, right? So maybe okay, and our break will be starting at 12:50. So like we have like around 10 minutes. Okay, so maybe I can show you guys how we can finalize the codes, right? And you will see that it's nothing really complicated. Just needs a bit practicing in programming itself. Okay.
Yeah, yeah.
All right. So we have to work on this place right there. And literally, what we can do, we can primary here think of how many symbols are we gonna analyze at this point. When we have the current one, we have a dash, and we have amount of repetitions. Overall, we have three symbols to work on. So once we will work on them, we have to pull the cursor after three symbols. So we have to increase I not by one, but by three. So that means that literally the best case scenario would be to split this increment of the symbol by one for every of the case when we analyze just one symbol, when we use just one symbol. And here, in the end of this code, we would be increasing I position by, well, the index position by 3. So we are working not on the one symbol, but on the symbol dash an amount of repetition that takes just one symbol. Is it clear so far?
Yes, I've done that.
Okay. Okay, and then let's get access to a symbol that literally stands on the third position after the current one, so which has the I plus 2 index. So here we will need to have the for loop. Well, let's call it index in the range, and here we create the array of well, primary, the text will have to be converted to an integer. That will be the primary one. And here we have to take the number after the number which comes after the dash, because this is the case when the next symbol is a dash. So next after the dash is amount of repetitions. Okay, and then what we're gonna do, we're literally gonna add a symbol which is the current one to decoded symbols, right? And we do that as many times as we have it's written in a symbol after a dash. Actually, that's only one of possible solutions. Let's see how that will be working. Yeah. So you see, we have original text, we have this text encoded, and we have this text decoded. So everything works well. Okay, so again, here we have our code. I will definitely share the file. So okay, maybe I can do that right now. So you would have the solution. And here you will have a link for this new file. So do we have any questions related to this code?
Please give me a minute.
Okay. A minute is
I,
up to you.
I
I
mean,
mean,
I've almost had it, but I didn't put that for index in range.
Okay,
Like
so
I
maybe
only missed that like one row.
all right. So you didn't know how to make this array which we are going through using foreign, right?
Yeah, I mean I know how to use it, but I didn't know like where exactly should I put it. I was trying to put after the first else in that if statement.
All
But
right.
yeah, that's my mistake. Like that's
Well, I saw that I pointed that exactly in this place you have to work on a dash and amount of repetitions. But okay, maybe you
I
had
was
some maybe
I was
things to
trying to do
decide.
the repetitions with like TT2 plus TTY plus TTY plus 2. Like I mean, but yeah.
Um. Oh yeah, that's incorrectly because okay, what else you could do? By the way, what else you could do? So you could avoid this for, and you could make a multiplication because remember how text works, right? How text multiplication works, right?
Yeah, yeah.
You could do
Yeah,
it even in
I was trying
section.
to do like that, but without the multiplication sign.
Okay, let's see if we will get the result, but we will get the result, yes. So this is just another way how to deal with this. Well, might we say it's an easy solution? Well, I suppose we could do that. So guys, are we good with this solution? Is it understandable for us?
I mean, for now, yes.
What about others? So we have Alexander connected and Rokus connected. So what would you guys say? Somehow from the beginning, the amount of students was doubled. So okay, only three survived till this time. Okay. So Alexander and Rokus, what are your thoughts?
Sorry, my English skills and very bad.
Ну
Я могу
хорошо, можете
по-русски.
по-русски сказать.
Да, вопрос повторите.
А как вы находите вообще вот эту задачу? Кажется ли она вам чересчур сложной или легкой, что там нечего делать? Вот как вы
Не,
считаете?
она тяжелая, но выполнимая.
Как я уже говорил, но тут, к сожалению, надо просто работать и пытаться, еще раз пытаться писать коды. Тут по-другому никак не выйдет.
Но я заканчивал Java программирование, там я как бы этот младший специалист. Так вот,
А, ну то есть с программированием у вас, в принципе, должно быть хорошо как таковое, да?
ну, более-менее.
Окей, вы работаете как программист или только закончили курс?
Нет, я только закончил. Ну, я так там на себя работаю по программированию. Сайты делаю, а
Ага.
так Java просто была возможность и закончил.
Ну, понятно, это все очень хорошо. Okay, and any comments from Rokas? You understand, but hardly. Um, yeah, unfortunately, it's not like I'm having bad news for you guys, but you need to practice, you need to try it, you need to code, and as more you will code, as more easier it will happen each time, actually. Okay, so as far as I see, we don't have any questions at this point. So maybe let's go then for a lunch break, and I will see you after a lunch break then. And we will take a look on Huffman trees. Well, Huffman trees is assumed to be one of most elastic and the most efficient method, by the way. But its programming will raise the problems. So maybe we won't be making the Huffman codes, but we'll be making the Lampel-Z-Welch algorithm. That's gonna be definitely happening. But that's about the time after lunch break, guys. So I will see you everyone after the lunch break. This session will be still opened. So our all classes would be in the one file, in the one video file. The only thing during the lunch break, I will switch off the microphone, and I don't know, maybe the screen sharing as well. Let's see.
Okay, see you after lunch break.
Okay, see you after the lunch break, guys. Like or continuing work. Edward, the only one connected. Are you here? Put a plus if it's so. Just really.
I'm here, but can you give me a second, please?
Yeah, not a problem. Sure.
Yeah, I'm fully here.
Okay, awesome. Right. So continue working. So we literally an encoding going to move forward. Okay. The next method. It has another name of the Huffman trees. Because it assumes a so-called binary tree creation. Do we know?
I'm sorry, you're lagging a little.
Okay, I'm lagging a little.
I
Okay.
don't know if it's my end or your end. I'm just a second gonna check.
Okay. How can we check?
I'm gonna check the router who's connected on it.
Okay. Okay. That makes sense. Anyways, I don't know. I have the icon that that connection is kind of well, but I don't know. I don't know. Maybe it depends on the server of this big blue button.
Yeah, maybe, but there's a possibility that my internet sucks.
Okay, okay, okay. So spend another minute to check it.
I don't know, I should be good.
Oh, if that's good, then let's just try. Can all right. So the next method, as I already said, is the Huffman trees. Do you know what the binary tree is?
Not really.
Okay.
I don't.
Did you have any course related to Introduction to Computer Science or something like that?
Yeah, we did. So probably.
Okay, it's really interesting why you didn't have the binary trees.
I just
Uh,
googled it. We did have it.
okay, Okay, you had it. Okay, great. So basically we will be preparing the binary tree. Well, something like the binary tree, and that thing will help us to form so-called a dictionary for converting symbols. Makes sense, right?
Yeah, yeah.
The only question, what will be those values of this tree and how we will structure them? And here we have kind of a pretty huge description about this method, but let's go in details. Uh, within within an example. So we have, let's suppose, some text, and it contains only specific symbols. Let's suppose it contains only 5 symbols: A, B, C, D, E. Can we imagine such text?
Yeah.
Okay. So we get to calculate um, a percentage appearance of a symbol inside the text. So for example, 10% like we have for the A, that means that every 10th symbol is A. So that means if we have 100 symbols, so 10 of them will be A. That makes sense, right?
Yeah.
Okay, and we get to place these values, I mean, with those letters and the percentage of appearance into the array. And that's going to be a one-dimensional array that has both of parameters for each of its elements. So next we have to sort the array in the cascading mode. So it means on the left side we will have the biggest appearances, and on the right side we will have smallest appearances. I suppose it's nothing complicated, right?
Yeah, it's nothing complicated.
Yeah. So the next thing, we have to take two last appearances, two smallest appearances, and we have to combine them. So if we had CA, so now we have AC or CA, you can call it differently. Literally, we have combination of two symbols, and their overall appearance will be combined. So it will be 0.16 plus 0.10. Result is 0.26. So right now you have these B, D, E, and AC elements. So in this case, you have one element less in the array, but the last element is being combined. So it's a combination of two. And now you have to resort the array, and you have to repeat operation. Does it make a sense?
Yes, yes.
So in the end, we do that till the case when all of the elements are combined, and their appearance is 100%. So I suppose you already got where's the key thing here. So this one element which has the 100% appearance, that will be the root of the tree. And literally every leaf of the tree is calculable as elements which appeared in their combination. For example, A, B, C, D, E root has leaves of A, B, C, and D, E. Because A, B, C, D, E was the combination of A, B, C, and D, E combinations. That makes sense, right?
Yeah, yeah.
So we have to go through all of these combinations, and we have to create such binary, kind of the binary tree between them. So that leads us to the case when we have final leaves which have a probability of exactly that letter which was included into the combination. And then we have to name the left path as 0 path and the right path as 1 path. So that makes it possible to find out the binary code for an exact letter. For example, letter A. what path, what key code will it have? It will have 0, 1, 1, because the region from the very root to that leaf takes the path of 0, 1, 1. And we create this dictionary, so A will mean a 0, 1, 1. Does it make a sense?
Yes, yeah.
And literally, since we created the dictionary, literally we can say, well, overly, the work is being finished here. The last thing is that we are going through the text, and we're going that from the left side to the right side going. And what we're about to do, we're about to take a symbol and find out that symbol's path code. And we just have to replace that symbol with the corresponding path code. So if we have this dictionary, which we have right there, so here we will receive the encoded text in bits. And honestly saying, frankly saying, here we are working with symbols, and more efficient this algorithm is working with binary codes. But let's take a look on its efficient level for the symbols, which is far away from being the best case. So we have 10 symbols, so literally that's at least 10 bytes. And if only we have this 10 bytes, how do we convert that? How do we compress it? If we will take a look how many bits we'll have here, well, let's count how many of them we have. So we have 2 bytes and 6 bits. Well, let's say it's almost 3 bytes. So the pure efficiency of this algorithm is around 70%. So 70% of the original data volume is being just compressed. So we got this, right?
Yeah.
Yeah. So and now you can think of taking whatever WinRAR or whatever other tool, and you can always check the compression level. And I might be wrong, might be, but from my experience, not every case reaches the 70% of compression. Is it so?
Probably yes.
Yes, exactly. Because sometimes we don't even reach some maybe 20%. Because the method which is used matters actually. All right. So as I said previously, every method assumes both encodings and decodings. So how the decoding works? So we have the same dictionary as we had previously. And what we're doing, we are collecting symbols, we are collecting bits starting from the left side going to the right side. And what do we do? Well, once we collect each next bit, we take a look if bit combination corresponds to one of the key codes from the dictionary. And once it corresponds to, then we take corresponding symbol and we write that in the decoded text. And then our so-called temporary memory is being erased, and we pull to that the next bit from our encoded solution. And in the end, we receive decoded text, or better to call it decompressed.
Okay.
So that makes sense, right?
Yes.
Okay, cool. So the only thing, well, actually, that's it about this method. The next will be the Lempel-Z-Welch. But anyways, talking about these Hoffman trees, this method is assumed to be called as one of the complicated methods. But it's really useful. Well, another question is, well, can we implement one? And since we will have trees, it means that we will have to use recursion and recursive functions. And I suppose that might be a bit complicated for your group, because well, literally the previous method shows that it will be far more complicated actually. So
I agree that's gonna be hard.
yeah, that's gonna be hard. So that's why we are passing this method at this moment, and we will be moving to another one. So Lempel-Z-Welch algorithm. Did we hear something about this method?
No.
No. Oh, okay. Well, this method is a really famous one, and it's been rephrased in a lot of ways actually. So when you will see the algorithm itself, well, you will understand this from the first eye shot, I think. Maybe we can move to the example because it will be much easier to understand this. So here we have encoding or compression. So idea is the following. You have initial values or initial text you would like to compress. So in the buffer, you take the next symbol, like that will be the first one, B. And here you have yellow area, which is encoded text, and the green area, which is the temporary dictionary. So the question is, if you have this B into dictionary, initially you don't have it. So you put that inside and you give to that as a number 1. And you place that B into encoded text. Then you take A and you check if A is in the dictionary. No, it's not so you place it inside, given the number for that, and you place that A into encoded text. Then you take another A, but A is already in the dictionary. So you add another letter, which will be B, and you have AB. So since you have more than one symbol, so you have to check if all these symbols, except in the last one which was added, is in the dictionary. And well, the reason why the symbol was added was that besides that symbol, that text was in the dictionary, right? Because A was in the dictionary. Is it so? Yes, it is. So what we do, once we added that B symbol, we literally find out A's number in the dictionary. That's going to be 2. So instead of AB, you have 2B. And you place 2B in the dictionary. Does it make a sense?
I got confused.
You got confused. So the thing is that to replace combinations of symbol chunks with the numbers from the dictionary.
Okay.
For example, here we'll have 4 symbols, A, triple B, right?
Yeah.
So optimization or let's say compression works in a way that ABB from this ABBB will be replaced. And instead of 4 symbols, A, triple B, you will have, let's find out A double B number, it's 4. So instead of 4 symbols, you will have 4B. So you will have 2 symbols.
Okay, I got it. Yeah.
And literally, that's the overall principle of this method. So yeah. So again, you just collecting symbols. Still the case when overall text is not in the dictionary, and you replace almost all of this text except in the last symbol with the number of that data chunk, and that's it. So what you have to work on when you do that? Well, you have to have original text. Frankly saying it so. Then you can make, let's suppose, an array of texts, which is frankly saying very simple to do because you can use the least editable sequence, right?
Mm-hmm.
And you can literally find out if the text is inside that sequence, right?
Yeah.
Exactly. And you can use such functions like index to find out the text's index in the array. Okay, do we understand what we have to start this method from?
From the beginning, making that like 1v.
Okay,
And
from the
then
beginning, making two functions, decode, encode, right?
yeah,
Given the text. And I really recommend you to take this text so you would be able to compare your input and your output because it's already here. You can check if you did everything correctly. Okay, so do I understand correctly that you don't need any recommendations at this point, right?
no, wait,
Or you need them?
of course.
Of course. Okay. So in this case, let me erase a couple of things here.
But basically, we can use like almost the same code. Yeah.
No, it won't be working.
No.
Well, I want to say that here it might happen that you would more likely use while instead of for. Yeah. So anyways, start with something like this. It will be much easier for you just to structure the beginning of the code at least. Okay, and here you will need to somehow go through the symbols, and you will need to have a dictionary. A dictionary will be needed to be structured in every operation, like encode and decode. They will be the same dictionaries, but they can be just formed once you run it, so you don't need to store it somewhere else. Okay, so what do we need to do? Well, we can use I as the current symbols index, and you can use the while to go through the array. So literally, you can go through the text in a such way. Surely we could print these symbols, and maybe I will write them the same as I had here. So that's gonna be B double A, B A, triple B, double A, quadra B, double A. Okay, so I have it. And I'm gonna run the code. Okay, so what was missing? The missing was increment of incrementation of I. So I will become I plus 1. Just to make sure that we increase in the index. Yeah, and we see that we are capable to literally access each of these symbols. What's gonna be next? You have to have the dictionary, which gonna be an array, right? Editable array. And you have to have a text collector, which gonna be this one. And literally, what you're gonna do nextly? Nextly, you're gonna literally add a symbol to a collector. So collector will be a collector plus a symbol. And in the end of the iteration, you will be freeing up a collector. So it could be something like this. All right. So what's gonna be nextly? Nextly, you will need to check if you have your symbol inside a dictionary. How can we do that? So if our text is inside the dictionary, because the C in D gives you true and false results, or you can just use it as the following. So it can be not, it could be whatever. But anyways, if C is in the dictionary, then you literally have to add another symbol, right, to the to our collection, isn't it? Is it so, guys?
Yes.
Yes. So literally we can say that, well, in this case, we just increase an I, and that's it. And there could be another case, the else case. How the else case will work? Well, the else case means that this collected symbols, they are not in the collection. Okay, well, since they're not in the collection, we will need to do something here. So we will need to take first, texts from the collection besides the last symbol. So so how to do that? Good question. But actually, if we would try to think of values of the sequence, we remember that we can have sequences made in a what way? That's gonna be something as the following. So you have a collection that starts from the beginning, and you have and you're going till the last symbol, excepting it, right? So literally, you are erasing everything besides the last. So you are erasing last symbol, or you're accessing to the text without the last symbol, right? Is it so?
Yes, I guess.
Yeah. Yeah. And then we
Okay.
have to. Yeah. Any question?
No, not for now.
Okay. And then, since you received that thing, you have to find out its literally a value or its index in the dictionary, right?
Mm-hmm.
Okay, let's call it I2, like, or C2 index, for example. Well, how can we do that? We have a dictionary, and we have to use the index function, and we're using C2, so we will find out that index. And then, if we found this out, so what we're gonna do? We're gonna have our encoded text as the previous text plus an index that's been converted to the text, plus we have to have the last symbol. So how do we get the last symbol? That's gonna be index of -1. Is it so?
I guess so.
Well, and once we do that, well, we finished working with our collector, right? So we are freeing up collector, and we are moving forward through the symbols, through the actual symbols.
Okay.
Mm-hmm. All right, all right. Well, let's see how that works. Oh, index and the original text. Well, something. The original text is original text, encoded text, decoded. Okay, where was I wrong here? Where was I wrong? So we have this encode and we have index. Hmm. Or maybe it was index of. Give me a second. No, it has to be an index. It has to be an index. It shows the error because yeah, the C2 was the empty. Okay, makes sense. Yes, makes sense. Okay, so let's then analyze what we have. So somewhere we get the problem. So we have these collectors. So we collect each next symbol. All right. If C is inside D, then we increase in I. Initially, it's not really so the else case should be working. So we have this C2, and we're getting literally a text without the last symbol. Okay, so what is missing here? So what are the basic functionalities we didn't include in this code? Who can tell me? Because there are at least two aspects we had to be working on.
I don't know, maybe sorting?
No, maybe something related to a dictionary itself. So we are checking if value is inside, but we are not adding the value inside, right?
Yeah.
Exactly. Okay, so what's gonna happen here? Well, primary. In which cases we can run this code? In cases when C2 is something besides empty text, right?
Yeah.
Okay, and it happens when we have more than one symbol in the C, right? Is it so?
Yes.
Yes. So what could be the solution? The solution could be to split the functionality for the cases when we have one symbol or we have more than one symbol. Is it so?
I mean, we could try, but if you say it's probably gonna work.
But no, take a look. We take everything besides the last symbol.
Yes.
If that's empty, well, then what we are looking for in a dictionary, right? There's nothing to look for.
Yes.
Exactly. So it means we have to have an if statement that will literally work in the case when the length of the collected symbols is more than one or less or not more than one, right? So if it's more than one, then it will be such thing. And there will be the else case. And the else case corresponds to the case when we have only one symbol. So what should we do right there? So here we will find this C2 index searching for a value in the collector. So that means that we take that one symbol and literally, we look for that one symbol in the dictionary. But again, in both of the cases, dictionary itself is empty, right?
Yes.
So what should we do?
I don't know.
You don't know. Okay, but if we will try to think, what was the algorithm here? If something is not in the dictionary, then what are we doing?
Go to the next one, create a next one.
No, we're adding value to the dictionary. You can take a look even on this one, A triple B. It's not in the dictionary, so we add it fully in the dictionary, right?
Yes.
Exactly. So that's what we are gonna do. So here in the else case, before searching for something in the dictionary, we will be adding the full collection of symbols into a dictionary. How to do that? Well, we will be using function append, and that's it.
Okay.
Another question is, did we place this pooling text into the encoded one in the correct place? And that would be correct when we have more than one symbols in the collector. Frank is saying that will be working nicely. It would have to work nicely. But if we have only one symbol and it wasn't previously in the dictionary, then do we need to find out that that symbols index into the dictionary? No, we wouldn't need that at all. So what we will be doing? We will be just placing that symbol to the encoded text, as I just did. And that will be totally fine. Does it make a sense?
Yeah, I mean it does, but why couldn't we just put it in a dictionary if it's one?
But we already put it.
Okay.
So nextly, when we will reach to this symbol again, this part will be working. And to the symbol which is known by the dictionary, or symbol sequence which is known in the dictionary, we will be adding to that sequence the next character from the original text. And when we do this, what we will get? We will get such encoding. Let's and Frank is saying let's well, maybe I will put spaces in the end, so it will be easier to get this chunks of symbols. Let's oh, you know what? Since here the index is being started from 1, and our array's index is starting from a 0, I will increase it by 1. And now we can compare what we did have in the solution, right, and what we received in the end of the script. So BA, 2B, 3B, 1A, 4B, 5A. So did we receive the result?
You did, yes.
Yes. I like how you highlighted you did.
Yeah, because I'm just watching, like, I'm not typing as you are.
Okay. Yeah. So anyway, so we are going a symbol by symbol. We are pulling each next symbol into the collector. Once we reach the symbol combination which is in the dictionary, we just go further to the next symbol, which will be added to the collector. Otherwise, we add what we have to the dictionary, And if our collected symbols added right now to the dictionary is more than one symbol, then we find out everything besides the last symbol in a dictionary. We find its index, and we place into compressed text the index found out in a dictionary plus that symbol. Otherwise, when we have only one symbol, we just put that to encoded text. And in both of the cases, we free up a collector of symbols and we move to the next symbol in the row. Okay, do we need this code?
Yes, please.
Okay. Okay, I put the link in the chat. Okay, do we have any additional questions about the solution of the encoding? Well, is there anything else I could help you describing how it works?
I mean, it's kind of understandable. I'm just, I mean, I understand. After you explained it, where you put it in the dictionary, I got it.
Mm-hmm. Okay, and what's about your colleague, Alexander?
Повторите вопрос.
Ну, вопрос такой, понятен ли вам алгоритм сжатия по методу Лампл-Зевелч?
Ну, я пока что-то не очень смотрел, я потом видеозапись посмотрю, потому что что-то с ребенком-то занят.
Окей, хорошо. Хорошо, просто я сейчас буду давать задание делать декомпрессию данных по этому методу. Ну, поэтому, ну, как бы, как обычно у нас сейчас практическая часть будет. Ну, хорошо, если так получается, без проблем. Okay then, so let's return to our things. So yeah, so you have this file, and now what you can do, you can try to use the same principle. Actually, the same principle will be needed, but right now you will need to have a decompression. Frank is saying how the decompression happens. Let's take a look on the method. So we have these chunks, right, which could be split and which could be separated somehow if you like. In my case, that was the space in the text. And what you do, you take each of these chunks, and if you have a symbol, let's call it maybe letter, then it just comes to the dictionary fully, and it comes to the decompressed text. That goes for B, then for the A. When we reach the case when we have an index and a symbol, then we find out that indexed value into the dictionary, and we add corresponded text to the symbol, and we add the result into decompressed text. Does it make a sense?
Yes.
Mm-hmm. Okay, so as you can see, it's almost the same as we have in our file. The only it just works in a different direction if we can say it like that.
So basically, we can use the same while code.
I would
and
say
just
yes.
and just
I
like
would say yes.
and just change some of the signs.
Yes. You can use the same wall and you can just change something there. I won't tell you from the very beginning what exactly you should change, but keep in mind that you have chunks of data, right?
Mm-hmm.
Because in my solution, you see these chunks of data being separated by the space. In your case, it could be separated maybe by something else. That's totally up to you.
Okay, I will try.
Okay, so we're good with it, right?
Yeah.
Okay, so I will open you this one, this example of decompression. Well, and since you have the file, so I think there is no need to open you the sources at this moment, because you have
No.
them.
Yeah, it's good.
Okay, then please try to work on it. And again, I won't disturb you for some of the time, but afterwards I will ask you about your progress, and then let's discuss what we have and what we don't have. Okay, so
Okay.
please start working on decompression method.
Okay. I'm not getting anywhere.
Okay, so let's take a look then on some of the a bit a bit let's say easier. So the first of all, we have to work on chunks of data, right? Is it so?
Yes.
Yeah. So we have to split them. Okay, so let's work on that firstly. We're gonna work on the collection. Maybe I will be working with the while loop again. So I will have the while loop. I will be increasing index all the time, and then I will be probably doing the following. So here the story is super simple. If only we don't have the current element as empty space, then if it's not so, then we are adding that symbol to a collection. There is else case, so literally otherwise, what will happen? Otherwise, when it's the space, well, we're just moving forward for two symbols, and when we got the symbol, then we go for one. It could be something like this. Okay, well, the story is simple. So once we reach the empty space, or you know, it could be even different. It could be the empty space. Let's maybe make another condition. So if that's empty space, or we reach the end of we reach the end of the index. So we reach the end of the text, like we located on the last symbol. Then we will be working on the chunks of data. Yes. Something like this. Otherwise, we'll be just adding additional symbol to the collection. Okay, but once we reach the end of this, wait a bit. If we reach the end, then we would need to read that symbol. So if we are in the end, then we will add a symbol to the collection. Yes, something like this. And we would need to analyze all the previous collection which was previously created, which was previously read. Well, primary, you know, guys, we can print these things out. Just, you know, showing that we have a collection and we have, well, and that's the exact chunk of data we have to analyze. Let's see if that will be working. So, what we got here, oh, we didn't free that up. So here in the end of the working on the collection, we will need to erase that. We will need to free that up. So let's see that again. Okay, so we have these values, but we have in addition that space. So how can we erase that space? Um, hmm. Okay, if only the current symbol is this one, or it's this one, or we're in the last position. Looks like here we have some problem. I will just add a point to see that, yeah, so literally this space is somehow added. So firstly we have to work on this one. Firstly we need to work on that one. Because it happens not from this side, but looks like it happens right from here, that adding the space. And that's gonna be the first one which has to be which has to be fixed. And here we have these two spaces, as we can see, which again is a good question why it happened that way. So this is the first thing which we have to work on. I don't know, maybe I will put here the brackets. Maybe there is something problematic with this condition. Maybe it's been understood incorrectly. Well, no, result is the same. Result is the same. So let's add here not the point but exclamation sign. And what we will have? Exclamation sign is here. Oh, we have the space. So that means that we have the space in the end. Okay, so literally, if we have the space in the end, let's just make this work till the space. Yes, let's just make this work till the space. Okay, so somehow I thought that in the end I don't have a space. Okay. Okay, so now we have to just take this one out. Okay, does that space appear? Okay, so that space appears only by the comma. Yes, okay, that's understandable. So once you put a comma in the output, that means that's gonna be a space in the output. Okay, so what else is going on here? We have chunks which this position are being written into the C. Okay, so it means that here is that line we have to be working on. Okay, and literally here we can already organize the work which is related to dictionaries. Well, we can create a dictionary itself before this code. So we can use the same D here, and here literally you can make the code. And for example, if C is indeed, then we will have one code, and the else case, that's gonna be some another code. Okay, for example, if C is not in the dictionary, then we can just, add that to the dictionary. Or there could be something else done. So the question, could you continue from this point, or it looks over than complicated?
It looks more complicated.
All right then. Okay. All right. So we can erase this part. So here, literally, the work should happen in the following way. If we have only one symbol, that means that, well, it can be just in dictionary or it cannot be there. So there are not many options for that. But if we have more than two symbols, then we would need to take out the number and the symbol out. So by the number we will get element from a dictionary, and the symbol will just, and the letter will just come next to the found in the dictionary. So here I would strictly split two cases. So let me write this. So if len of C is bigger than 1, that's gonna be a case for one thing, and another one will be if we have not more than one symbol. So if we have not more than one symbol, then it could be just in the dictionary or it could not be there. That's it. Not many options left here. So let's maybe firstly implement this part, and then let's go forward to another parts. So if well, primary we add an text into decoded one. It's one thing. Another thing is if not C in D. So if it's not in the dictionary, then we are appending that one to the dictionary, like this. Okay, so that means if I will run this code, I will get first B and A as decoded texts. Oh, okay, so something happens with the else. Okay, I need to write some equation there. So I will get oh, okay. Before I return, I free the triple T2. So yeah, let's run it again. Oh, so T2, if that's the space. Ah, okay, this is gonna be erased. That point, yeah. So yeah, so I have this B and A. That will be these two chunks, which are try to be found out in the dictionary. Does it make a sense, guys?
Yes.
Okay, so the rest chunks literally contain more than one symbol. So it's two symbols where a priori we know that the first one is the index in the dictionary, index plus one, as we remember, and the second element, which has index one, is the pure symbol that has to come to the array. Sorry, to the decompressed text. So this means that here we will make a pure split. Pure split of what exactly? Primary, again, we will need to work on this part firstly. Well, no, andly. Like this one. But before that, we have to work on this C. So, a priori, when we reach this case, the first letter will be number in the dictionary. So that literally means that we can rewrite the chunk of data as a chunk of data of the -1, which means the last symbol, or just one, if you like, to call it that way. And before that, we will have to add information from the dictionary of the index, which is an integer value of the first symbol, like this one. and in the end of that action, after appending the result into the dictionary, we have to add the same result into the decoded text, and literally that's it. So there's nothing overcomplicated, I would say. So if we would run this, what would we get? Okay. So we have problem right there. So integer. Okay. Maybe I need to make the conversion somehow differently. But no, it has to be in integer. It has to be integer. It has to be an integer. Okay, don't really get why we have. Oh no, you know what's the problem? Maybe I'm accessing. Oh no, actually I access it normally. It has to be using the square brackets. Okay, what it shows us? Listing is list index out of range. Well, it comes before because the minimal index was the 1. So for the array, the minimal index is 0. So we have to decrease it by 1. Yeah, so literally that's why we have this problem. So if we do that and we try to run the code again. Okay, first I need to convert and then I need to decrease. So it should be that way. Okay, let's run it. And as you can see, we have decrypted text, decompressed, and that's the way how that's doable. So, do you have any questions about the solution?
I mean, it looks easy when you do it. I can't just figure out how. There's so many stuff going on, but as I said, it looks quite easy. But we just need practice.
Exactly. Yes. Exactly. Okay. Then I will send you this code, right?
Okay.
Okay. So I'm sending you this link to the chat. So you have it.
Yes.
All right. All right then. So yeah. So just the leftover Welsh material. Well, literally we overlooked that algorithm. Well, might be nothing very specific. Okay, and another thing looks like by the time schedule, so we will be having the break before that. Okay, so let's take the break and let's work after the break then on certain algorithms.
Okay. When are we coming back?
After 10 minutes.
Okay.
So literally at 30 minutes we are starting going through those sort of algorithms.
Okay.
Okay, let's take a small break. All right, so I think we can continue working. All right, so as we talked, we already finished those compression methods. Okay, maybe it's not maybe not very successfully, but still, and I really hope that more or less it's understandable how these methods have been organized. And now I suppose we can go for the next things. And the next thing will be give me a second. Maybe I told you in a bit incorrect way what we are gonna overlook right now. Oh no, it's still better to start with certain algorithms. Okay, so the question for you guys, do we know any certain algorithms that allows to sort the array?
We probably do, but we cannot name them now.
Okay. So it was some time ago, right?
Yes,
Okay,
like
so
a year ago.
so I open you a section with several links. Well, oh, wait a bit. Wait a bit. Looks like oh no, it has to be opened. Yeah, it has to be opened. All right, so we have that link, and maybe let's take a look on those methods, and let's see how they work. So they will be quite simplified solutions. But anyways, let's see them, and let's think of their implementation. Okay, so here we have literally an information about these methods, but literally what we'll be doing. This link contains several methods. But I would like to show you them maybe in a bit different order, and we'll be starting with the bubble sort, which assumed to be as one of the easiest methods that could be for sorting. Oh, oh, that's super unexpected. So looks like they moved the page. At least previously they had super cool descriptions about these methods. Give me a second. I will try to find those examples somewhere else. Okay, I just got the ads in the video. Okay, wait a bit. Yeah, I found this out. Okay, so here we will have a video material, then again some ads like all the time.
Lesson 1, Bubble Sort. To follow along with this lesson, you will need some basic knowledge of algebra. The bubble sort is the simplest of all sorting routines. In this context, sorting means ordering an array of data elements such as integers. To begin, imagine that we have an array of elements that we wish to sort. We use an empty array here for illustration. The bubble sort algorithm can be described as follows. Compare the first two elements of the array and swap them if they are out of order. Continue doing this up the array for each pair of adjacent elements until we reach the last entry. At this point, the last entry is the largest element in the array. In the bubble sort, we continue this procedure for each next largest element until the array is fully sorted. Now, we'll fill in the array and show the algorithm in action. We begin by comparing the 5 and the 9. Since 5 is less than 9, we do nothing. Then we compare the 9 and the 2. Since 9 is greater than 2, we swap the entries. We continue just as we did before. Notice that the largest number, 9, bubbles up to the end of the array. This is where bubble sort gets its name. Once the 9 reaches the end of the array, we start the next pass and continue through the rest of the algorithm and sort the entire array. The pseudocode for the bubble sort algorithm is very simple. It's just the 4 lines shown here. Bubble sort is a slow algorithm. To quantify what we mean by that, we calculate the time complexity.
So, so next there will be the time complexity. But the time complexity is just the way how do we specify approximate amount of operations which is needed for the method. Such measurements, they're kind of normal thing for comparison different algorithms, different methods, and so on. Okay, let's take a look on such measurements for this method.
Suppose that we have an array of n elements. During the first pass, we perform n-1 comparisons to get the largest element to the end of the array. The next time, we perform n-2 comparisons. Continuing, we get the following sum. This is an arithmetic series which sums to n times n-1 divided by 2. Now n times n-1 divided by 2 is equal to n squared divided by 2 minus n divided by 2. For large values of n, the n squared term dominates. So we say that the algorithm is big O of n squared. Eventually we will formalize this concept of big O, but for now we'll just leave it at this.
And literally that's it about this bubble sort. So did you know this method before?
We knew probably the first part.
Okay, so what do you mean by the first part?
I mean, where it was the smaller numbers without the letter n.
Okay, makes sense. All right, so the algorithm itself is known for you, right?
Yeah.
Okay, so in this case, the task for you will be to implement this method into the Python.
Okay.
Yeah, so firstly you will try to do this, and if you wouldn't manage, then we'll do that together. Okay?
Yes.
All right, then try to do this, and once you will get your codes, maybe you can just post them in the chat. But please, guys, try to work individually, and if your colleague posted something, don't really try to get those codes. Try to write your own codes. Yeah, exactly. So make the array, make it be filled with values, write a certain algorithm and run it, and see if you have correct results. All right. So please start trying making this. Okay, so I said that Edwardus, you send the code. Okay, let's maybe wait for some other solution a bit, at least a bit. Okay, so the question for Mindaugas and Alexander. So how is it going with this bubble sort for you? Okay, makes sense. Makes sense. Thank you for the answer. What's about Alexander? Probably it's impossible to work because according to what I heard previously, it looks like Alexander, you're a bit busy with the family stuff, probably. Okay. All right. Well. I don't know. Maybe let's make this method together then. So let's maybe take a look on that meta code which we had previously. So what it shows to us, it's just one of implementation of the bubble sort. Here we're going from the here we have indexes of the array that start with a 0. And we literally go from literally we compare indexes which are mentioned by the letter j. So letter j goes from 1 to I minus 1. Literally that means that this I value literally what's the essence of it? Literally it's amount of repetitions for which we're going through the array through the variable of j, but at the same time each time we go for another repetition through the array, we analyze for the one element less than previously. And then we compare aj and aj plus 1, and if they are located not in the predicted order, then we swap them. So literally how that could be happening in the Python. In the Python, as we know, we can work on the for-in for the range. But at the same time, as your colleague even wrote, the range can be made in a pretty different manner. Edward, okay, internet helped you. Okay, makes sense. Makes sense. So let's make then this one together, because okay, so we will have the array. That's gonna be some values. Well, I don't really care which values we will set there up. For example, something like this. Let's suppose, and we will have the sorting method. So primary, we have to go through the array, and if we go just once, right? What will happen? How can we do that? So we have for-in, and then we have to mention those indexes we will be working on. Okay, how to do that? So we will be working, let's suppose, for indexes in let's suppose the range between 0 and let's suppose n minus 1, right? And by that we will be getting access to every element we have. But since we need to operate with okay, let me make a variable n that has five values, 5 elements, amount of elements. So, and we will be having, let's suppose, the range of n minus 1. So by that we just accessing each of the values, as you can see. And if we will run it, you see we're accessing the elements except in the last one. So why we did that? Why except in the last one? because actually we have to be capable to have an index plus 1, because we have to work on pair of elements. So you see, so right now what we can do, so we can make the following. So if we would like to have, let's suppose, a scattering sorting for the array, then it means that if on the left we have the element which is bigger than element on the right, I will change this index to just a regular I value. So if I is bigger than I plus 1, then we have to swap them. Okay, and then we can literally print out the array. Okay, so what will happen in that case? Oh, I did something incorrect. Yes, the A is up. Is a lowercase. Okay, I have to change the letter. Print A. Yes, the uppercase should be used here. Okay. So you see, right now this 57 is being just pulled in the end of the array. So that means that how many times do we need to go through the array? Overly. So one time to have the last element, then another time to have the pre-last, one more time to get the pre-last, and actually one more time to work on this pair of values. Okay, looks great. So literally, in other words, that means that it's gonna be equal to amount of elements minus 1, right? That's what gonna happen. So which means that if we have here a j, which is about to be amount of repetitions going through the array, then it will be working. And let's see if that will be working. So you see, right now it's being sorted. But the problem is that each time we go through the array, we go through the arrays, through the beginning till the end and pair, which is not really needed. So since the j value varies between 1 and 4, we can take this out from the range of elements we are gonna work on during each next going through the array. And since j starts from a 0, then all is good. So right now, let's see if that will be working. And yes, so we have this result. So in reality, here we have these 4 lines that literally is the same as we had 4 lines here. So does it make a sense, guys? How can we implement this method? What would you say? Okay, great. So do we need this code?
I don't know, yes.
Okay, then I will send you this. And here you have it in the chat. All right, so let's go further and let's take a look on the next method, which is frankly saying a modification of the bubble sort, and it's called insertion sort, or as it's called in a so-called IT slang, the stone sort. So let's take a look on this stone sort, as we call it. Okay, how can it be without adds? Okay, let's wait until the ad will be finished.
Lesson 2, Insertion Sort. The insertion sort is somewhat similar to the bubble sort in that we compare adjacent entries and swap them if they are out of order. Unlike the bubble sort, however, we don't require that we find the next largest or smallest element. Instead, we take our next element and insert it into the sorted list that we maintain at the beginning of the array. In this example, we will use an array for illustration. However, the algorithm works for other types of linearly structures such as linked lists. We use white to indicate the elements that have already been sorted, and a light gray to indicate the element that is being inserted. Beginning the insertion sort, we can consider the first element as our starting sorted list. Since there's only one element, we can consider it sorted. Then we move to the second element and compare to the first. If they are out of order, we swap them. Otherwise, we leave them alone. At this point, the first two entries comprise our sorted list. We then go on to the third entry and so on. In general, we insert each successive element by swapping it with the one before it until we reach a smaller element. Now we'll demonstrate the insertion sort on an array of integers. At any stage, the insertion sort has a set of sorted elements and an element that is to be inserted. We begin with the first element equal to 24. Since this is only one element, we consider it a sorted list of length 1. Next, we insert the element 13, which is in the second place. Comparing 13 and 24, we see that they are out of place, so we swap them. Now we have a sorted array of 2 elements. We move on to insert the third element, which is 9. Comparing 9 to 24, we see that they are out of order, so we swap them. Then we compare 9 to 13. Since these are out of order, we swap them also. Now we have a sorted array of 3 elements. We move on to insert the fourth element, which is 64. Comparing 64 to 24, we see that the elements are in order, so our fourth element is already in its proper place. Now we have a sorted array of 4 elements. Going on to insert the fifth element, we have a 7 there. Comparing this element to 64, we see that they're out of order, so we swap them. In fact, 7 is the smallest element so far, so we'll move all the way up to the beginning of the array. Now we have 5 sorted elements. Moving on to the sixth element, we have 23. This is smaller than 64 and 24, so it gets inserted before those. With 6 sorted elements, we move on to the seventh, which is 34. 34 is smaller than 64, but bigger than 24, so it gets inserted between them. Now we have all of the elements sorted except the last one, which is 47. After 2 comparisons and 1 swap, the entire array is sorted. Insertion sort has an advantage over bubble sort in that we only need to make comparisons until we find the location of the element in the sorted list. This means that unless the array is totally backward, we will make fewer comparisons than bubble sort, and if our array is already sorted, we will only make n comparisons. A convenient aspect of the insertion sort is that the method can be used to add new elements to a sorted array at any time. In fact, this is how you will most often see insertion sort used in practice. We will give an analysis of the time complexity for insertion sort later. For now, we will just give the pseudocode for the algorithm. We begin with a for loop that loops over the index of the entry that is to be inserted. Then we run through a while loop that performs the insertion. The while loop swaps the inserted element with the one before it as long as it is less. This concludes the lesson.
Okay, so is the method itself is understandable for us?
Yes.
Okay, so let's take a look again on that metacode which was provided. Okay, let's find this out. Where was it? Okay, yeah, right here. So idea here is the same. So we go through the elements, but in this case we go through all elements of the array, and for every element we have a small array left behind between the initial element and the first one. Sorry, before the initial element, or let's call it the second element of the array, and the current position. So literally, each of those elements, they are kind of checkable with their neighbors. And idea is that if previously we compared the current element and the next one, so here we compare the current element and the previous one. That's why we start going from the second element. So there would be at least one element behind that which we can include into comparison. So that's one thing. Another thing, so there is a need to swap the elements. It means that potentially we would need to swap elements till the end of that sub-array, going to the beginning of the array. Literally, that's the principle of its work. And since here amount of operations strictly depends on the values themselves, so this method in the ideal case can okay, let's call it the average case. So in the average case, can cost less operations than the bubble sort. Okay, so that's the idea of this method. Okay, so can I ask you guys to try to implement this method?
I mean, yeah, we can try.
Yeah, especially you have all of these codes with you. They're available. So at least you can try to make it. Okay, so please guys try to implement this method.
А можете повторить, что надо сделать с этим вашим заданием?
All right, so I see that there is no any single submission in the chat. So how is it going with this method?
It's okay, but I have a question.
Yeah, go ahead.
Like on the YouTube video, it says for I equals 1 to n minus 1. This does
Mhm.
not work for me. I had to look up and I found out that I have to use in range, like for I in range 1 to n, and the other is with the swap. In YouTube video as well, there is a swap, but I don't know if it's just an old video or something. I had to manually swap it.
What do you
Like,
mean? What do you mean by the old video? What do you want to say by that?
I don't know. Like, I don't know why it's not the swap function. It says that it doesn't recognize it. I don't know.
Okay, then I will ask you another question. Which programming language is this code written in?
Probably C++, maybe
No, not at all.
C
It
sharp.
just no, not at all. It's just a meta language,
Okay.
which just shows you ideologically what you have to do. Which means that every function which is written, you have to find equivalent for in
Yeah,
the
I
language
understand now.
which you're using. Well, I already showed you the swap method. So here you have the swap method between two
Yeah, I
values.
used it from this.
Okay. And where else do we have a problem?
No problem at all.
No problem.
I
Okay.
used basically I used a lot of stuff from your previous code, so it helped.
Okay, but still no result, right?
There is a result. Everything's fine.
Okay, but you didn't send that.
I'm sorry. I will do it now.
Because I was just waiting if someone will post it. Yeah. Okay. Okay. Mhm. 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 Um. Yeah. Looks correctly. Looks correctly.
Yeah, I just got confused that for I in range 1 to n. Like I wrote n minus 1 and then didn't register and I've got errors and stuff. So I was looking up for the answer.
Mhm. Well, n-1 there was um yeah, actually why isn't it n-1? Why? So why is it just n? Okay, let's run the code. Let's see if that's working. Yeah, it gives the result, but why it's not n-1? The range. So what will it give us? What this range gives us? A good question. Let's then print this out and let's see. 1 and 4. 1 and 4. 1 and 4. Then we have a j. Okay. If j is bigger than a 0. Okay, this one is correctly. But why it's not this one? Okay, well, what else we can do? We can print a value of I, like this one. And let's see what it gives us. It gives us 1, 2, 3. 1, 2, 3. If that's gonna be a 0, that's gonna be a 0, 1, 2, 3. If you would make this experiment, you would see that literally we are given a value, right, or an index till which excluding we will get a range of values, the same as when we specify a range of indexes for a sequence, right? That's why this n-1, it's the value which is not gonna be taken into account by the range function of the Python.
Okay.
So we have to give here n, which will mean that we have the range between 1. Okay, I will write this in a such way. So between 1 and 5. I think you get these brackets, right?
Yeah.
So including 1 and excluding 5. But anyways, if we would be thinking about indexes, we have to reach the last index. And surely we start from the first one, right? As it was in the original code. So it was 1 and n. So from 1 till 5 excluding 5. And then we have results. Okay. The question for others is Edward the solution clear for you? Okay, great. All right, so we have half an hour left. Okay, the question: do we still have a power for overlooking materials?
Do you have what? Sorry.
Do you have a power to continue working?
I mean, do we have a choice?
Okay, then let's take for today the last method, and we will be just. Okay, Mindog tries to read my mind, but it's a bit different. But it's a bit different. But in the same narrative. Okay, so I suppose that we can then finalize today's classes with overlooking one another method in a very fancy way shown by one of the bands. So I will ask you then before the next class, which will happen on Friday, to think about that method, right? And maybe try to make a solution. Okay?
Yes.
All right. Maybe it sounds very very interesting, right? In a bit maybe unusual way. But let's see. But let's see. But let's see how it looks like. Okay, I hope that I copied the correct one, and I think you will like this, guys. But again, it's just an example of the certain method. And again, we will have some ads, so let's wait till its end. Okay, so as you can see, those guys make a lot of these dances that represent some algorithms. Well, I find them really, really interesting ones. Okay,
Yeah, that was fun.
yeah, it's a really cool one. Yeah. All right. So before we will finish, so did we get what those hats represented?
I mean, from the name of the clip, it's a quick sort.
Okay, no, idea is about those hats. Maybe you have seen that those guys took a hat, right, and danced only those who had hats, right?
Yeah.
Yeah. So literally, those are two indexes of elements, which are about to be compared.
Okay.
So literally that what was represented by hats. And for each of the ranges, as you have seen, the hats were passed to the middle of the current array between those numbers which were compared. So, and if we swap elements, then we change direction of the index, which is gonna be um, um, modified. So left index go to the right side and the right index goes to the left side. That was the idea. Okay, so yeah. Actually, I don't have a full kind of description about this, just written theoretically, but I have one practical example. Maybe I can give you that if it's been uploaded. Ah, no, I didn't upload this. Okay, maybe I did that in another course. Give me a second, I will take a look. Hmm. Hmm. Okay. So I got those pictures. So here I have the scan from one of the books. Okay, well, this book is is in Latvian, but it doesn't really matter. So here we have the following. So here we have the starting area, and we always compare indexes that comes from the beginning of the range and the end of the range. And initially we decrease the right index. Well, let's call them A index and B index. A can be only increased and B can be always decreased. I think that makes sense, right? Yes or no?
Yeah.
Yeah. So once elements stand in the necessary order, and our order is a cascading order. So on the left we have smaller value, on the right we have bigger value. So once it's so, we work on the current index, and current index in the beginning of the range is always index B. So we decrease index B. Once we swap elements, we swap the index which is going to be changed. So now when we swap the 3 and 2, we start to work on index A. So you see index A is being increased. And once we swap those elements, 5 and 3, now we started to work with index B. And it's being all the time decreased. And once A and B becomes 1 value, so you then this tree stands in its location, in its exact location after the full area is going to be sorted. So this tree took its location. So on the left side of this value, we have some values, and on the right side, we have some values. And we have to work with both of those ranges in a similar way. Surely here I have continuous of this method. So looking on the left side of the tree, okay, we sorted that correctly. And looking on the right side, and okay, here we fix this 4 in its position. Then on the left it has nothing. On the right it has the range, and we are working with this range. And as you can see here, we continue working with this, with every of those small ranges we have. And literally that's how this method works. Does it make a sense?
Yeah, it does.
Okay, so let's do like this. So at this point, then we are finishing our classes, and you will try to do this on your own before our Friday's class. Okay?
Okay.
And on the Friday, since we have only one class, we will be just continue working with the sorting methods. Because it's just one class. Well, what else we can do during just one class?
Okay.
All right then. So thanks everyone, and wait a bit. I will take a look. I will take a look on the chat. Okay, in the chat we have nothing. Okay. All right, guys. Maybe it's time for Q&As before we will finish. Do we have any questions so far?
I don't think so.
Yeah. So only practicing is needed.
Yeah, that's for sure.
Okay. All right, guys. So it was nice to spend this day with you. So on Friday we are continuing a bit, but what we can do? Yeah. So try to implement this algorithm before our next meeting, and then again we are rushing in the coding. Okay, guys. Thanks
Okay.
again, and see you on Friday.
See you
Bye-bye.
Friday.
Have a
Bye.
nice day, guys.
Bye.